Let's jump right back into it. This is Mechanical Features, Gauges and Sensors, Part 2. Welcome back to the explainer. So let's do a really quick 15-second recap of Part 1. We know that radiators cool things down using thermosiphon, and tap changers adjust the voltage in discrete steps, safely operated off-load only when completely de-energized. Right, so that's the baseline. Now, let's look at the dashboard. And right off the bat, here's an awesome rule of thumb for you out in the field. Generally speaking, oil-immersed transformers commonly use a 7-step tap range, whereas your dry-type units commonly use just 5 steps. Why the difference? Well, oil-immersed units are usually out handling much wider incoming voltage swings on longer feeders. Dry-type units are usually tucked away indoors, much closer to the source where the voltage is inherently more stable.
Okay, so this brings us to the actual monitoring equipment. Look, gauges and sensors aren't just passive little accessories. They are the transformer's active dashboard. I mean, think about it. You wouldn't drive a car down the highway with your fuel and temperature gauges totally taped over, right? But crazy enough, a lot of sites just completely ignore their trending data until a massive alarm actually fires. We've got to shift our mindset there.
And that's exactly where the P100 sensor comes in. These are platinum resistance temperature sensors. The brilliant thing here is that they sit directly at predicted hotspot locations deep inside the winding, not just bobbing around in the bulk oil. It's an absolutely crucial design choice because it's that localized hotspot temperature, not the average oil temp, that actually cooks and ages the insulation over time.
Let's put this into perspective with a real-world scenario. Say you've got a 2000 kVA unit, and its hotspot is trending at 98 degrees Celsius against a strict 105-degree limit. At first glance, 98 degrees is under the limit. You're probably thinking, hey, everything's totally fine. But actually, if that number steadily climbs 3 degrees a month and your electrical load hasn't changed at all, you have a serious problem brewing.
The absolute number might technically be fine, but that upward trend line, it's literally screaming at you that something inside the tank is generating abnormal heat. Reading that dashboard trend catches early insulation degradation months, and I mean months, before a static alarm or a protection relay ever sees it. By tracking those changes under a flat load, you're fundamentally shifting from just reacting to a failure to proactively extending the transformer's life.
So let's do a quick interactive check to tie all this mechanical stuff together. Imagine your incoming utility supply fluctuates by plus or minus 7%. And let's say you have a standard 5-step tap changer that adjusts exactly 2.5% per step. Here's the big question. Can you fully and reliably correct for that swing? Just take a second to do the math in your head.
The answer is no, not really. I mean, sure, 5 steps theoretically give you a 12.5% range, but in the real world, installations rarely run perfectly pinned at their extreme top or bottom taps. When you're fighting a 7% swing on a 5-step changer, your operational buffer is incredibly marginal. This is exactly when and why you'd specify the 7-step oil-immersed configuration instead, giving yourself some actual breathing room. Okay, so look at that. You've essentially mastered the fundamentals here. You can now confidently read a transformer's mechanical fittings and explain precisely what every single component protects against out in the field. You've got radiators for the cooling, tap changer step rules for the voltage, and pressure gauges paired with those PT100 sensors acting as your early warning dashboard.
Next up in the explainer, we are finally going inside the sealed tank to look at the iron core and the copper windings that are doing the actual electrical work. But I'll leave you with this thought to chew on. If the external fittings have to be this robust just to manage heat and voltage variations, what kind of immense, violent magnetic forces are we trying to contain inside that core? We'll dive into that next time.